Great. Okay. Good morning, good afternoon from wherever you are, whenever you're watching this. Welcome to the next Water, Wetlands, and Watersheds seminar. Today, we're very lucky to have Dr. Leonardo Bertassello talking to us about wetlandscapes. One word, wetlandscapes. So get prepared for this. It's like wetland landscapes, but it's more efficient. So Dr. Bertassello received his PhD in civil and environmental engineering at Purdue University. That's where he first began developing these stochastic hydrological models for how wetland and wetlandscapes work. He has since expanded his research to focus on ecological dynamics driven by that hydrological foundation and which species can inhabit wetlandscapes when and where, using metapopulation models and network-based approaches. I think we'll hear about that today. He's currently a postdoctoral researcher at Notre Dame's Environmental Change Initiative, and sounds like you're going to pivot a little bit to focus on water resources and human communities, in particular the resilience of human communities as a function of how, when, where, and how resilient the water system is. So we'll be happy to have you next year also for another talk. Until then, Leonardo, the floor is yours today. Please go ahead.
Okay, so I'll start sharing the screen. Can you see
Perfect.
everything?
Looks perfect.
Okay, so thanks David for the beautiful introduction. So hello everyone, I am Leonardo Bertassello, and as David said, today I'm gonna talk a little bit about wetlands and metapopulation. But first of all, let me start by saying a few words of thanks to all the friends and colleagues that work with me during this year, because without their help, suggestion and support, this project, this research will not have been possible. So let's get started. Global climate change is contributing to significant shifts in the worldwide distribution of species. And as a result, predicting species response to global climate change has become a common goal to several disciplines. And perhaps no class of species is more emblematic of these changes than amphibians, which have suffered a dramatic loss worldwide over the past 4 decades. Indeed, amphibians are among the most climate-sensitive taxonomic group because they are exposed both to a terrestrial and an aquatic habitat at different stages of their life cycles. At the same time, wetlands, that are one of the most critical habitats for amphibian reproduction, are also extremely vulnerable to climate shifts. And for this reason, we start to think how we can associate the amphibian decline with climate change in the hydrological regimes of wetland. This is of course not a novelty, as it's pointed out here from these 4 or 5 papers. But what we were feeling that was missing, that was lacking, was a strong integration between the 2 worlds of ecology and hydrology. And so we started asking ourselves, what could be our contribution? Because what we want to do was to provide a kind of eco-hydrological synthesis to characterize and predict amphibian population dynamics in response to climate-driven changes in wetland hydrology. So I think the first time we started thinking about how to do this, I was here at University of Florida, sitting with Jim Jawith in his lab, and we were reading this Nature paper by Munepira Kul about the fish diversity on the Mississippi River Basin, and trying to picture how we can extend this work for our purpose. Then after a couple of months, I went back to Italy, and I had the chance to talk with Enrico Bertuzzo and Andrea Rinaldo about their last recent paper about their spatial explicit approach to model the metapopulation dynamic for a species. And after several discussions among all of us, we are feeling that a possible research gap that we will be able to address with our idea, with our framework, could be not only to consider how the landscape structure, in this case, the wet landscape structure, is an important determinant for species persistence and landscape connectivity. But what we wanted to do is to integrate also the temporal dimension of hydrological variability in play. Indeed, some of these earlier research were kind of assuming the landscape as an static environment where species could disperse and migrate. However, we know that wetlands are extremely dynamic systems due to the temporal fluctuation of their volume, their stage, and their size. So we decided to integrate this temporal hydrological variability in our ecological framework, starting from the hypothesis that amphibian or other species of interest may persist in a landscape, even under temporally non-stationarity forcing or heterogeneous landscape habitat, if and only if they are able to access a number of suitable and diverse patches. So in this analysis, it is clear that wetlands have a central role and are the key subject of this research, because they are indeed the habitat where species, and in particular amphibians, can live, breed, migrate, and reproduce. So now I'm not going to give you a strict definition of what a wetland is, tell you why they are important, what is their function at local and regional scale, because I believe that everyone in this audience knows well about that. Instead, what I want to do is to better explain how I'm going to conceptualize a wetland in this study. So here, wetlands are viewed both as an hydrological and ecological unit. From an hydrological perspective, wetlands are dynamic objects scattered in the landscape, and that's why they are called here wetlandscapes. And whose attributes such as stage, area, their separation distance change in time based on the interaction between the climatic forcing and the soil properties. At the same time, wetlands are also fundamental ecological habitat because they serve as home to a wide range of flora and fauna. And in addition, and a very important thing in this study is that these wetlands should not be considered isolated component in the landscape, but they should be think as connected through an ecological network where species can move from one habitat, from one wetland to another one, once that the conditions are not more suitable for them. So keeping this in mind, in the next slides, I'm going to focus on three major topics. First, I want to show an eco-hydrological model that is able to assess and investigate the spatiotemporal hydrological variability in wetland attributes such as stage, perimeter, or size. And then, given this hydrological variability, I will present a dynamic metapopulation model to assess species persistent and the ecological connectivity in this wetlandscape. And finally, in the last part of the presentation, I'm going to apply this eco-hydrological framework to a real case study. So the first step, as I said, consists in investigating wetland hydrological dynamics based on the impact of hydroclimatic forcing, represented here by precipitation and evapotranspiration, wetland bathymetry, as defined by the landscape topography, and the hydrological connectivity through a shallow groundwater. And here are the two mass balance equations, one for the wetland volume and one for the groundwater volume, that I'm going to use in this approach. So the first term on the right-hand side of this equation is the rainfall contribution due to a series of rainfall events over the wetland contributing area. And at the same time, we have also this recharge process driven by infiltration in the root zone to the volume of the groundwater. Then the second term on the right-hand side represents the water losses due to evapotranspiration. And these fundamental terms links the wetland volume and the groundwater volume exchange of water through the wetland perimeter. A very important thing about this model is that here it can be applied both at the local scale of the single isolated wetland in the landscape, but also at the landscape scale, because if we conceptualize all the wetlands scattered in the landscape as independent unit, we can run this mass balance for every one of them, and so we can predict their dynamics. And from this perspective, I'm going to apply the previous mass balance equation to these two case studies. These two pictures represent two very different wetlandscapes of the United States, one in the North Dakota Prairie Pothole Region and one in Texas Playa Lakes. Why I choose these two case studies? I choose these two because they are characterized by the large number of isolated wetlands that can be considered as an ideal case for landscape patches where species can migrate. And also because they are located in two very different hydroclimatic regions, one more dry and cold and one more warm in Texas. And so given these two very different wetlandscapes, we run the previous hydrological model using as input actual data for precipitation and evapotranspiration. And we assign the soil property of each wetland based on the dominant wetland soil listed in the soil surveys database. Here, I'm presenting the result of the hydrological model at the landscape scale for the two previous case studies, both in terms of wetland normalized area and wetland separation distance. The former variable is defined as the total wetlandscapes normalized area, which means that we are computing for each time step the total wetted area divided by the total maximum wetland area. So when H star is equal to 1, it means that all the wetlands in the landscape are full of water at their maximum capacity. Instead, when H star is equal to 0, it means that all the wetlands are completely dry. So this 2-time series, actually this 4-time series, shows high variability between the annual wet and dry season, with the heavy rainfall events that are translated in the expansion of total wetland area and a simultaneous decrease of the mean separation distance. Because as the wetland expand, the separation distance among these isolated objects is, of course, decreasing. What is also interesting to observe is how in the Texas landscape, the mean separation distance among the wetlands is very large if compared to the one in North Dakota, showing how North Dakota is a more dense landscape, while in Texas, they are more isolated and more far apart. I've decided to show you the result of the hydrological model in terms of wetland separation distance and wetland area for a specific reason. Indeed, these two variables are of key importance when we want to create a network of wetland where the species can move across. And we are using network theory here to better explain the connectivity between these nodes. And this technique is widely adopted in several sciences, such as transportation system, brain network, and social network. So what we want to do is also to try to apply this interdisciplinary approach to our case studies. And in our eco-hydrological framework, the wetlands become the nodes of this connected web. And the connection among these nodes, which is clearly a function of the separation distance, become the edge of this network. And in particular, the edge, these links between nodes, are present if and only if there is a potential flux conceptualized here by the movement from one species to another, from one wetland to another wetland. And here we can have a first example of the potential structure of the wetlandscape network. Once we have defined the structure and the topology of the wetlandscape network, it's also fundamental to quantify the degree of connectivity among wetland nodes. And for this purpose, we select a certain number of network metrics to assess the status of the wetlandscapes. And among these, I choose two: node degree and node betweenness. In the central plot here, there is the node degree that quantifies the number of links that are incident to a node. So if a wetland has a node degree equal to 5, it means that there are 5 wetlands connected to it. On the other hand, here I'm plotting the node betweenness, and with betweenness, we quantify the number of time a wetland acts as a bridge between the shortest path between other two wetlands. So here, large betweenness node serve as the stepping stones to favor the dispersal of species. And in this example here, we can see that the red wetland, that are those one characterized by a large value of betweenness, compose a kind of eco-hydrological corridor that can be taken by species to travel across the entire network. It's like a highway for frogs in this kind of sense. However, what this slide shows is only a single snapshot for a static wetlandscapes. And for our purpose, this was not enough. This was not enough because in the previous part of the talk, I showed you how wetlandscapes are extremely dynamic systems that fluctuate in response to the hydroclimatic forcing. So the novelty we are introducing here is that the stochasticity driven by the hydroclimatic forcing is now translated in the stochasticity of the network connections. So wetland size, shape, and separation distance change at every time step due to heavy rainfall event, because the wetland can expand and shrinks during more arid conditions. Some of the wetland can disappear and the separation among these wetland changes. And these dynamics cause a modification in the topology and the structure of the network and its metrics. And as we can clearly see here, this ecological corridor is not static, but is changing in times. So this slide here shows the result of network metrics dynamics for the North Dakota Prairie Pothole region that I showed you previously. And what we can see here is that the temporal dynamics of the network metrics, like mid-node degree and mid-node betweenness, is strongly affected by the rainfall seasonality, with peaks during the heavy rainfall event. And what we can see here in these maps is that during dry condition, there are very small value for node degree and node betweenness. The network tends to be very much fragmented and with low value of node degree and betweenness. Instead, with intermediate wet condition, we can see that these two values tend to increase. We can have more cluster of this wetland, and the network is divided just in a couple of subnets. And finally, during wet condition, both node degree and node betweenness increase because wetlands are getting more water. And in this case, we can clearly see the emergence of a cluster of wetland and the ecological corridor that I showed you before. And these information are extremely important when we want to better understand the emergent ecological pattern that can be sustained by this landscape. For example, wetland cluster here, that are those wetlands characterized by the large value of node degree, can indicate the location in the landscape where a group of species with similar trait, with similar dispersal ability could congregate. On the other hand, this node betweenness map can identify those wetlands acting as a stepping stones that allow to maintain viable species population by favoring their dispersal. And all this information are extremely useful from a landscape management and conservation perspective, because the loss or the disruption of this wetland, either from climate change, either from land use alteration, can decrease the available habitat and therefore the connectivity of the landscape, which at the end can drive species to the extinctions. Okay, so in the last part of this talk, I'm going to focus more on the species that actually lives in this wetland habitat. Indeed, this riparian zone, these wetland edges, are key habitat for species such as amphibian that are more associated with water and wetland than are most of the reptiles, birds, or mammals. And therefore, amphibians such as frogs tend to be distributed in the landscape in patches as a metapopulation. And the term metapopulation is widely adopted in landscape ecology to define a group of spatially separated population of the same species which interact at some level. And a very important index that we can consider for better understanding the suitability of a given landscape to host amphibian community is the metapopulation capacity. In the classical metapopulation theory, the metapopulation capacity is able to capture how the landscape complexity, here defined by the patch habitat and the spatial configuration, on species persistence. In particular, larger is the value of the landscape metapopulation capacity, more this habitat is able to offer a suitable landscape for the species of interest. This K index can be evaluated as the leading eigenvalue of the patch landscape matrix, whose element Mij are defined by the size of a given pair of wetland, their interpatch distance, and the dispersibility of the given species, which is modeled here as an exponential decay function of the given distance between the pair of wetland. Our main contribution here is again to consider this metapopulation capacity not as a static value, as in the classical metapopulation theory, but dynamic, given the hydrological variability of each wetland, which we have seen in the previous part of the presentation, that affect largely the size and the interpatch distance of these wetlands. And finally, to simulate the movement of species from one wetland to another wetland, I've used a spatially explicit model called SPOM. The acronym SPOM stands for Stochastic Patch Occupancy Model, and the name comes from the fact that we are not going to model the abundance of species in each wetland, but rather the probability that one wetland can be occupied or not occupied by at least one individual. The two equations here represent the probability that an empty wetland will be occupied in the next time step. And on the other hand, this equation here, which is the probability of extinction, models how an occupied wetland can be unoccupied and then can be empty during the following time step. The two processes of colonization and extinction are here driven again by the size of the wetland and their dispersibility. And what is interesting is that during dry condition, where some of or most of the wetland will be constrained into a smaller size, we can expect that the probability of extinction increases because here an inverse relationship between the extinction and the wetland area. And these represent the main novelty and the reason why this model is called dynamic SPOM instead of static SPOM. Because in the previous study, the SPOM was applied by conceptualizing again the patches as a static environment, and maybe sometimes removing some of these patches using some criteria like a random removal or target removal. Instead, what we are doing here is to consider the loss or the gain of wetland in the landscape just driven by the spatiotemporal variability in the hydrological conditions. And this fundamental difference is represented here in this slide. What we can see here is that given the hydrological variability in a wetland attribute, we simulated using both the static and the dynamic model, the metapopulation capacity and the average occupancy in the landscape. We can see here that for each stochastic jump in the wetland area induced by the rainfall, both the metapopulation capacity and the wetlandscape occupancy increase as well. And then during absence of rainfall, during more dry condition, we can see this gradual recession due to the gradual habitat size decrease and the increase in the gap distance. What is important here is how we compare the static and the dynamic model. We run also the static model just by conceptualizing the wetland as fixed at their average area. And what we can see here is that the two models are able to capture or are able to reproduce the same mean occupancy value. But the main advantage of the dynamic model is that it is also able to capture the variance in the metapopulation capacity and average occupancy. And this is especially clear here in the North Dakota wetlandscape, where the static SPOM, the red line here, severely underestimate the fluctuation, the temporal fluctuation in the occupancy. And this is extremely important when we want to monitor and assess the population dynamics. On the other hand, here in Texas, we can see that both the static and the dynamic model during the first 3 years show more or less the same result. However, the big difference is that after these 3 years, we observe a very long, very prolonged dry period, and only the static model is able to tell us how this dynamic in the hydroclimatic forcing can be translated in also variation in species occupancy, because we can see that the occupancy in this landscape severely dropped from 0.65 to 0.25, just because of the contraction in wetland area and their increase in the wetland distance. So to test the reliability of our approach, we were able to find actual data for species dynamics that were very helpful to tell us how we were doing, if the model makes sense, if we are able to reproduce this dynamic. Because so far, I've just shown you some model simulation. And now what we want to see, are these simulations correct? Are we doing a good job in describing and framing our approach? So the available data here were obtained for a 20 years period of monitoring in the Cottonwood Lake Study Area, which is a cluster of 16 wetlands in the Prairie Pothole Region of North Dakota. We use these monitoring data, both the available data were both from an ecological point of view, because we were able to collect these data for rana pipiens presence, rana pipiens abundance, and also the hydrological variability in this wetland, these 16 wetland. The data, as I said, are available for a 20-year period of monitoring campaign, and were collected at weekly for the hydrology and monthly level for from May to September of each year. So first, we use this data to calibrate our hydrological and ecological model. And then, given these calibrated parameter, we also run the experiment to a much bigger wetlandscape, which is presented here, and is characterized by a 20 by 20 kilometer and included more or less 5,000 of wetland. And we have done that because we want to account for the spatial heterogeneity of the landscape, how we can also affect species presence and persistence. So here, there are the results for the hydrological regimes in these 16 wetlands of the Cottonwood Lake Study Area. The hydrological variability, the hydrological regime is characterized again by a strong seasonality in the forcing, with heavy rainfall event during the summer and during the spring, because it was following the snow melt. So during this period, you can see a large increase in the wetland area. And after this, we will see a drop in the area due to the increase in the evapotranspiration process that exceeds the precipitation. And the contribution of the groundwater in this region was very small. What we can see here is that on average, the total wetlandscape area was pretty much stable during this 20-year observation, and how the numerical simulation of our hydrological model was accurately reproducing the observed pattern, both from the time series here and in the cumulative density function. What we have done is that, based on this calibrated parameter, we also run the model at the 400 square kilometer landscape scale. And again, we can see here the pattern in wetland area and wetland separation distance, and how they are strongly affected by the seasonality of the forcing. What we have also done here, to understand better the spatiotemporal variability of the wetlandscape, was to take a 3-year period from the 2002 to 2005 and plot the wetland size distribution and wetland separation distance distribution for this short period. And what is evident in these two plots is how wetland size distribution is much more sensitive to the variation in the hydroclimatic forcing. And this suggests how in this complex and high density wetlandscape, the separation distance is not strongly affected by this, because even if during dry condition, one of the wetlands next to each other is lost, there is a probability another one that is still available for species colonization. So given the hydrological variability that I showed you in the previous slide, we run our dynamic metapopulation model, and we compare here the simulation, which are the gray lines, with the actual observation in terms of frogs dynamic. Again, the time series here shows a strong seasonality with larger value of occupancy during the wet season of each year, which suggests that the seasonal variability in the wetlandscape hydrological condition hugely influence the habitat suitability and the access to this suitability, which in turn drive the metapopulation dynamics. And what we have seen is that this overall persistence of wetland, wet condition in the Cottonwood Lake Study Area contributed to a likewise persistence of rana pipiens occupancy, because we can clearly see how this seasonal trend is also translating the seasonal trend of the rana pipiens. The comparison here between the observation and the simulation is also present in terms of probability density function. And here we can see how these probability density functions tend to be well described by a gamma distribution, which reflect the hydrological behavior of the landscape attribute. And as before, we run, given this calibrated parameter, we run the model at the landscape scale in order to observe how the dynamics can change from local to regional scale. And what we observe is that the occupancy variability observed in the 16 isolated wetland is at least twice as large as in the regional scale. And this difference between the regional and the local scale it suggests that the increased number and the increased diversity of wetland habitat at this larger landscape dampens the variability in occupancy and contributing to the persistence of the rana metapopulations. Finally, to assess the influence of this spatial heterogeneity on the metapopulation occupancy, we decided to run our model over 100 subdomains of the larger landscape. And each one of these is characterized by the same size of the Cottonwood Lake Study Area. So we took our big landscape, we divided it in 100 single realization characterized by the same area of the Cottonwood Lake Study Area. And we plotted here with the gray line, the probability density function of the occupancy. What we can see here is that the spatial variability across these individual realization is very large. And this is mainly related to the difference in the distribution of wetland area and separation distance within each subdomain, which highlight the huge spatial heterogeneity of this wet landscape habitat. And the ecological implication of such heterogeneity is evident here when we take a look at the metapopulation capacity. Here we can see that as the metapopulation capacity increases, we have on average a larger occupancy value and also a smaller variability in this occupancy. In addition, here I decided to highlight in reds those single domains that are characterized by the same number of wetlands, 16 of the Cottonwood Study Area. And this difference between these 8 domains, these 8 single realization, suggests that wetland size and how they are distributed are extremely important to determine the metapopulation capacity and the metapopulation occupancy. So to kind of conclude, to kind of summarize what we're talking about today, we can say that first, we saw a stochastic hydrological model that can be easily adapted at landscape scale, and it allows us to obtain wetland attribute of fundamental importance, such as wetland area and wetland separation distance. And these two variables are extremely important because they allowed us to run and to integrate static network approaches to determine the spatiotemporal variability in the wet landscape connectivity. And indeed, this landscape scale hydrological variability have fundamental and tremendous cascading effect on the aquatic habitat suitability and the emergent metapopulation pattern. And finally, we applied the previous dynamic ecological framework to a real case study, and we saw the validity of this approach and the importance of integrating the hydrological and ecological world of science together. Thanks for your attention, and I'm here, so we have a lot of time, I guess, for questions.
Thank you, Leonardo. Thanks so much for the presentation. And we will open it up to questions in the room, as well as from anyone on YouTube out there. I want to start you off with one question about, it's great talk, by the way. I love how you building from like in the theory all the way to the application from hydro to eco, and combining a lot of both applications as well as disciplinary knowledge. So you must have worked with a bunch of different scientists on this.
Yeah, that's why at the beginning I had to thank you a lot of author, a lot of people for their help, because we are all coming from very different. I mean, we are all kind of from the hydrology context, but what we want to do is, okay, let's try to see how these hydrological dynamics are fundamental for the ecology.
So thinking about that and like about, you got frog data probably from some, from wildlife biologists or ecologists, and, and thinking about conservation and the very like direct conservation applications of this work. Can you talk about like vulnerability or like identification of the most important wetlands, or like remove, like, optimization? Like, let's say we needed to destroy some, you can now tell us which ones to save, and, about sort of direct conservation applications.
Yeah, and I think that this is a very great question, and a very important answer can be found here when we are talking about the network metric, because this, wait, can you see the screen?
No, I stopped your sharing, but if you want to share again, you may go ahead. Yeah.
Okay, well. Okay. So as I was discussing during the presentation, I think that from a landscape management perspective, these could be the two main important and most important plot, because it is a clear visualization of what we were doing so far, because we can see, okay, if we are going to remove some of these red wetlands, so these nodes with high betweenness, what is going on is that we are going to disrupt this eco-hydrological corridor, and we can prevent the species from going from one point of the landscape to another point of the landscape. So it's very important to try to conserve these kind of wetland. But at the same time, we can not only look at this betweenness corridor, because we can also look at this cluster of wetland that is showed here by the node degree map. And what is important, maybe from a conservation perspective, is to be able to identify both of these wetlands, because we can see that it's not that they always coincide, the hubs or the stepping stones. So keeping in mind what is our priority, we can use these network metrics to better understand in which part of the landscape we are going to operate, we are going to create a new pond, we are going to favor the dispersal of some species.
Okay, thanks. And of course,
and the important thing also is that is not static, is not only in this moment, but what we can do is to average during a given time period and see on average what are the most important wetlands that allow the dispersal or allow the clustering of individuals.
Yeah, or you could, in dry times, the node betweenness changes, and maybe those are the most important for, even if you're going to augment water supply or something like for a critically endangered species, you could find those as being like the critical habitats to even support, much less, avoid destroying. So Matt, you have a question. If you want to ask, please go ahead.
Well, can I just ask a clarification about this analysis? Because I agree, this was the thing that stood out to me for like, if you were talking to a wetland manager about like what parts of the landscape to prioritize, this is a super useful information, because it, that's one of the things that's always been vexing about wetland protections, conservation reserve programs in places like this. But I wondered, there's a certain, I noticed when the node betweenness animation that you showed, that the wetlands in the middle of your selected domain were always the ones that had the highest node betweenness. And it made me wonder whether this method is sort of sensitive to the spatial extent that you're sampling. The wetlands at the edge of your study domain are almost always going to have low betweenness just by virtue of arbitrarily defining the boundary that way.
Yeah, that could be a problem, because, for example, is affected, of course, by the finite size effect of the domain we selected in this case. So another idea, which is also why, and also when we want to run the metapopulation model, because we had to run it to a larger wetlandscape in order to allow species from outside of the box to enter in the box. So this is also something that we need to take into account. But another important thing for this video is that this video is realized for a given species. So for example, for a species that has the dispersal ability of 200, 300, 400 meters. So as we increase the dispersal distance, and therefore the type of species we are interested in, we need, of course, to increase the domain, because this analysis can be good for a frog. But if we are talking about birds that have a much larger dispersal ability, we need, of course, to account for it and pick a larger domain.
You still want to ask about salinity as well?
Well, yeah, I just was, I mean, it's you know, these Cottonwood lakes, well, actually all the prairie potholes have this extraordinary heterogeneity in their salinity that's driven by the sort of extent of their hydrologic connectivity. And I wondered whether, I mean, it's not, you didn't really sort of consider evaporative enrichment, but that's one of the sort of outcomes of heterogeneity and hydrologic connectivity in that landscape. And I wondered if you know, I think you worked with David Mouchet with, I believe maybe these are his data.
Well, these are his data.
Yeah.
So I not worked directly with him, but it was extremely useful, the data that were available in the USGS website, because they were kind of a unicum, because it is always super hard to find. It's always super hard to find ecological data, and it's even harder to find these data at different moment of the year, because they were able to sample frogs for at least 20 years, and each month they were going in the field to sample this data. So this was perfect for our analysis, because we were in this way able to not only understand the inter-annual variability, but also the intra-annual variability. And this was just great.
Yeah, that's great. I don't know if you know David, but you should reach out, because I think it's been a labor of love his whole career is to do that monthly sampling. But yeah, no, it's beautiful the way that you frame it.
Yeah.
Oh, go ahead. Sorry.
No, we submitted this work to Landscape Ecology, and we suggest also him as a potential reviewer. So maybe he will appreciate the work.
But yeah, I mean, I remember talking to. Oh, go ahead.
For example, the salinity, this is not, of course, directly integrating the model, but I think that a very powerful thing about the D-SPOM approach is that here we made it a function of wetland area, basically, which is the I and IJ that is in the metapopulation capacity, or like, where is it? So here, basically, what we can do is to change, or at least weight the wetland area or the wetland habitat given a salinity. So instead of using just the area, we can say area divided by the amount of nitrogen, the amount of salt, the amount of anything that is present in this wetland. In this way, we can also incorporate these dynamics. And this can be also useful, or instead of weighting the area, we can weight the separation distance, because even if the distance is the same in between wetland A to wetland B and wetland A to wetland C, but maybe along this path, there will be an ecological barrier, there will be a bridge, there will be a road, or there will be a very wet habitat that can favor the dispersal of species. So not only weight the area, but also weighting the path for these frogs or these species to move.
Thanks, Leonardo. We have a question from Anastasia. She asks, what main criteria were behind your selection for the research sites in the Prairie Pothole region, and the Texas wetlands, and the major sort of similarities and contrasts between the two?
Okay, so we run so I show you here the result of only of two wetlandscapes. So the one in Texas and the one in North Dakota. However, in our work, we have run the same simulation also for other 4 wetlandscapes, one in the Florida Cypress Dome, one in the California vernal pool, Maine vernal pool, and the last one was in Minnesota, in Minnesota. So because we took this kind of same wetlandscapes of meta-analysis and on his paper on PNAs. So we wanted to do in analysis, try to take in all the most important geographically isolated wetlandscapes. But just for the amount of time here, I just wanted to show 2 extreme cases, in my opinion, because these are the Texas and the North Dakota, because as I show you, these are very, very different landscape, as we can see from their density, their maximum area, the heterogeneity in the landscape, the nearest neighbor distance, the fact that they are located in two very different hydroclimatic regions. So that was why I only show you the result of two landscapes, but we have the same analysis also for other 4 wetlandscapes of the United States.
Great, thanks. Keep it open to anyone else in the room. I'd like to ask you like a nerdy hydrological question, if you don't mind. And please, if anyone else, feel free to unmute or raise hand. So, you know, I know you work with Jim Jowitz, who is the big fan of the, oh, this is perfect, yeah, right. The elegant solution, right? Stochastic distribution models. And yet, of course, you still have some K1, you have some K2, and you said that you calibrate the model to the observed data. Whatever method you use, you have to optimize the goodness of fit or the agreement. So you calibrate it at the scale of the CLSA, and then you scale it up to see what happens. But at any point in there, did you leave any data out from the CLSA to validate? So you calibrate one time, you use all the data to calibrate and then apply, or do you validate the model? And I guess extending that question the same for the frogs, right? So the frogs also required validation or calibration, or did you just use a literature value for the frog can hop 200 meters? Or did you tweak the model to make it work?
Okay, perfect. So first, the hydrological model. So instead of going here and just going to the results here on the time series, maybe. Where is it? Okay, so here it is. So as concerned the hydrological model, I said we use actual rainfall data, precipitation data. And then what we have done is for each wetland, for each of the 16 wetlands, where we have data in terms of size, in terms of wetland stage, thanks to the known Van der Kamp and Hayashi relationship, we were able to move from stage to area to volume through the bathymetry parameter. So what we have done is to take first these size data and translate it in area data and calibrate or at least assess the topographic bathymetry of this complex. So we are able to get the 16 exponent for the power law relationship between these areas. And what we have done to upscale from the small site to the 5,000 wetland domain is to randomly sample these coefficient value and assign them to all these wetlands. And then we run the model just by using these calibrated value for the shape coefficient and the hydrological soil parameter, and run the model to see and then aggregate them in terms of the total area. Then for as concern the ecology part, so the SPOM model, what we have done is to calibrate the ecological model using these 3K parameters, which are E, which is the extinction constant, C, which is the colonization constant, and the K, which is the dispersal ability. So we calibrate the model for the 16 wetlands using the available data. And then we just run this model, keeping the same value of K, E, and C, because we say, okay, since we want to monitor rana pipiens and we calibrate this value, we are running the same model using the same parameter to see these same species, how we can do during these and along these bigger wetlandscape.
Yeah, I think that makes sense. And then when you develop the C, E, and K, you have some number, and like comparing it with a sort of gut feeling from this David that Matt talks about, like was the dispersal distance reasonable? Was the the extinction rate, like you have
a very tricky thing is that the dispersal ability is also affected by the density of the wetland, because maybe my dispersal ability, the frog dispersal ability is 1 kilometer. But if in 1 kilometer or in 200, 300 meters, I have already the habitat that I'm interested in, I'm not going to exploit my entire dispersal range ability.
Yeah, you need to do a frog challenge test out in the field, right?
Suresh, my previous advisor at Purdue, was always fascinated by this. And what he wanted to do is to put a GPS on top of each frogs to see how it's doing, because
hey man, you can do it nowadays. You can do it on insects. So maybe it'll be the next step. Any
Okay.
any last questions for Leonardo?
Can I ask a question about when you took the Cottonwood Lakes analysis and you scaled it up to the full analysis, you did the 100 realizations, it looked like basically you could get
Anything
any
can happen.
configuration of, I mean,
Exactly.
any
And this-
configuration of frogs. And I guess I wonder if you've vetted that result with like the biologists that know something about this northern leopard frog, and they know that, like, yeah, when you do surveys of this frog, you find it, it's patchy, but you can find it anywhere. It's really, I guess I found that to be a striking result that I'm still processing, and maybe you could talk a little more and I'll shut up.
Yeah, because in that sense, another slide that could be of interest could be this one. So I said that we run the model to the 100 single realization of the same size of the Cottonwood Lake Study Area, and this first bar here. So we can clearly see how there is a huge variability in the possible wetlandscape occupancy. And this variability is, of course, leveled off once we are simulating the model for a larger portion of the landscape. So we can kind of say, okay, maybe once we get simulation for example, here 8 by 8 kilometer with at least 1,000 of wetland, we are sampling from a kind of representative wetlandscapes, and from these representative size we can make prediction. Because maybe if we just make prediction based on the result of these 16 wetlands, we can say, okay, beautiful, Rana pipiens is perfect, is doing a great job, and this is what happened in the black line. However, if we pick another portion of the landscape and we run the same data, we can see, like, you cannot clearly see, but you have to believe me that in this case we have a complete exponential trend with very, very low occupancy of frogs. So we can say, oh, if we look in this portion of the landscape, frogs are doing great. If you look in the other, they are dying. So we need to find a trade-off, a balance to say, okay, this study is representative and we can make conclusion out of it. But again, I guess it was super hard to find data for 16 wetland, and now we are saying, hey, you should monitor it 1,000 wetland. Thanks, of course we should, but how can we do that?
I think this is a very important result, the one you have up here, though. It's sort of like, what's the characteristic scale of a wetlandscape that's meaningful to an organism that has a particular dispersal distance, right?
Exactly.
I think that's really cool. Anyways, excellent talk, dude. Well done.
Yeah, thank you, Leonardo. So thank you so much. Let's give a round of applause to Leonardo, real or Zoom version. Stick around, come back next week. We've got Dr. Sam Zipper, assistant professor from Kansas Geological Survey and University of Kansas in Lawrence. No flow, no problem. Drivers of flow and long-term change in non-perennial streams. These are these folks that love streams that stop flowing and are super excited to tell you about why they're so important. All right, we will see you next week. Leonardo, thank you so much for coming to speak with us. We'll be in, I'm sure we'll be
Thank you for inviting me.
Yeah, Leonardo, that was excellent. Thank you, man.
Cheers, everyone.